You guys ask me this question all the time. What flap disc should I buy? Well, to be honest, I have no idea. But that got me thinking, what if I could build a machine to figure it out? But not just that, I want to answer a ton of questions you don't even know you had. Questions like, why are some discs way more expensive than others? Will I get a better result with a high-end disc? Or should I just stock up on a bunch of cheap ones and see what happens? And what about shape? Why do they look the way they do? Does the number of flaps actually make a difference? Or is it just for show? And here's the big one. Every company claims their disc is the best. Can I just grab any old disc off the shelf and call it a day? Unfortunately, the internet's not much help either. Some reviews are glowing, others are total duds. So who do you trust? Are these reviewers experts, or just people like you and me? Do they even know what they're doing, or are they just grinding the wrong way? In order to answer these questions, I think I need to build a machine. So let me show you what I'm thinking. I'm going to start with a standard 4.5-inch grinder, something almost everybody has access to. I'll need to make it move back and forth, but I don't have the consistency or the energy to move it every time. So I'll have to secure the grinder to something that I can adjust the length and the speed of the stroke. I want to see what's happening with the disc, so I'll turn the grinder upside down. Then I'll need to find a way for it to grind metal, and then measure how much material gets removed, or simply the amount of time that it takes to grind. This will allow me to track each disc's performance consistently. Then I can repeat the test again and again with different discs, making direct comparisons. And of course, I'll be able to change up the test conditions to see how different discs respond to different variables. Time to put this idea to the test, so let's get started. I'm gonna have to start with the base, a solid foundation to build everything off of. This piece of 1/4-inch plate is going to work perfect for our base. The grinder can get mounted here. We can trim off anything extra that we don't need. All right, on we go. I want to move the entire grinder back and forth. I have a few ideas to get this plate to move back and forth. First is to have it ride on a set of rollerblade wheels, where the wheels ride on a piece of plate steel and it moves back and forth. But I'm a little worried that the wheels might deform and then create a lump, causing the sled to bob up and down. In order to avoid this problem, another option is to create a dovetail way, like a milling machine has. But these dovetail ways are generally designed with very little clearance in between, and I'll be doing a lot of grinding near it, producing a lot of grit. The likelihood of this grit getting inside these ways is high, and will cause the entire unit to seize up and stop moving. I like the idea of having wheels, and can solve the problem of the lumps by making them steel. I also like the idea of the dovetail ways, but the steel wheels will be able to easily roll over any grit or grime, so I think I'm going to combine both of these into one. And if I remember correctly, these already exist, and I don't have to invent them. They're called drawer slides. And the cool thing about drawer slides is you can mount them flat, upside down, or on their side, and they roll pretty good, and they're really cheap, and if they ever go bad, you can just replace them. This drawer slide extends way too far, so what I think we only need is this inner piece. So let's separate this piece from this piece. That way we have a much shorter slide that we can mount to our plates. Now we can cut this short. I want to weld these rails to this plate. If the rails get cockeyed like this as I weld it, obviously this isn't going to move very well. So what I need to do is space them. They need to be parallel, the two monster squares. You slide them to set the distance from this surface to this surface. You lock it together, a pair of pliers, and now they won't move. And now everything's gonna go in the right direction. Put a pin in here, line it up to the table. Now I gotta stop. I want this surface to run parallel with this surface. So we're just gonna use a spacer. Now I'm not twisted, and these can go where they want to go. Okay, everything still slides. Put a little light tacks in there. That should hold it. So that works. Look at that. So I could tack the front, tack the back. That's pretty slick, yeah? Editor, give me a fat beat. Oh yeah. This machine is going to make thousands of strokes back and forth, and I don't want to stand here to push it, nor would I be consistent either. I have to control how fast and how far it moves, so I need to figure out a way to push this. We're going to use some sort of motor like this one. This is a gear drive, 27 RPM. So how am I going to get this motor and this sled to move together? I want to turn rotary motion into linear motion. My first idea was to create a linkage with two pivot points, converting rotary motion to linear. That way this motor can push the sled forward. What's cool about it is if I change the length of his arm as it starts to spin, it's going to adjust how far the sled travels. The longer the arm, the longer the travel. So I'll have to pick a length. But the problem with that is that this arm lifts up and pulls, and then pushes down when it moves back. These forces put strange up and down loads on the drawer slides. In order to protect the drawer slides and remove the up and down forces, I need to remove contact from the sled and motor from the top of the stroke to the bottom. And I can achieve this by making the pivot ride in a slotted bar, connected to the sled. This is going to be simple. I'm just going to make a bushing that goes on the motor with a hole in it. It slides over the shaft and will have a hole in the snout that can hold a pin. The slot is just quickly created on the water jet out of 3/16 of an inch steel. All right, got our pieces cut, so let me show you how this all works and fits together. This plate will fit on the nose of this motor like this. I'm gonna throw it on with a couple screws here. This should be plenty strong enough to hold it in place. And then we'll prop it up back here with maybe a little support or something. We'll snug this up. And this piece gets welded right here. But where it gets welded right here is gonna be determined with this piece that we made earlier. It's our little snout, and here's a bolt. So what happens is, bolt goes through the slot and into the end of this like that. These set screws go on the motor. We snug these up temporarily so I can show you how this works. There, like this. We'll tack it all together and then we'll cut it apart if it doesn't work. Okay, let's test it out. Let's see if this thing slides back and forth. It's so stupidly simple. Oh, it's torquey too. I don't think I could stop it. There's no way I can stop that. Ah, that is strong. That's gonna plow through some metal. What's really neat is this motor is variable speed. Check out this dial, low and high. I don't know where it should be set yet, but we'll play with that a little bit later. I'm guessing we're gonna have somewhere around 20 strokes per minute. And to quickly attach this grinder to the base, I robbed the holder from a previous video, cut it off, and attached it to my grinder. But before I mount it to the rig, I need to know the material that I'll be grinding. This is gonna be our test bar that we're gonna be grinding, going on the edge of the disc right here. See how we have like 3/4 to 1 inch of grinding material on this one? So as we oscillate forward and backwards, we should be getting good coverage. Any more than that, we're just wasting time. But we need to hold this piece of material vertically right around here, and in a way that we can see what's going on right here. This test coupon needs to be fed into the grinder with gravity that pulls it down. But since this grinder is moving back and forth, it wants to push the coupon forward and backwards. So I need a way to secure the coupon so it always remains vertical to the disc and doesn't move back and forth or side to side. So here's what we got. I cut a whole bunch of pieces. So we'll weld these together and then weld them on the ends. And then we should be pretty dang close to getting finished up. Take a look at this. This is a cool thing. So I'm about ready to weld this on, but see how I have this little offset right here? You flip it over. See, more clearance. Ta-da, just like that. Okay, this guy needs to be square. So as I was putting these all together, I started thinking, what's better than one grinder? Two grinders. So that's what we're gonna do. I think I have enough room to do dueling grinders. I think it'd be cool. This is really gonna speed up the process. I got the grinder mounted, got this little jigamadrew all set up, but what I really started looking at is my little bracket right here. And what I was hoping for is that when I put this in here, that the grinder would be able to tilt and project this surface of the grinder perpendicular to this rod, which means I want it sitting like this. Why do I want it sitting like this? Because I would like this rig to be able to test the two types of flap discs. One is a type 27, which is flat, and the other is a type 29, which is conical. That means that the coupon is colliding with these discs at different angles and could result in unequal grinding. So I will have to be able to change the angle of the grinder depending on the disc that's tested. So I need to elevate this bracket up probably almost 2 inches so that the grinder can sit like this. And then we can raise and lower the back of the grinder depending on what we're doing. We can build some sort of adjustment screw and a strap or something. But every disc we can change, and then we can alter the height right here. I added this little tube so that we can go up or down and change that. So what I'm gonna do is I'm gonna cut these brackets off and I'm gonna set them on top of this 2-inch tube. That should give me the elevation that I need. I like to just tack everything because you never know if something changes, and I can just quickly grind them off in case something doesn't work. So now, as you can see, that when this rides back and forth, see how it's running nice and flat? But when it's tilted like this, look what's gonna happen. See, it wants to lift, fall, lift, fall. So it's gotta be like that. And we'll make this adjustment for every disc. So this is a flat disc. which this would be back here, and we begin grinding flat. All right, so here's what I came up with to adjust this. Now I try to keep this as simple as possible. I'm in a hurry. I'd love something really fancy with an adjustable slot and angles and a whole bunch of grid and a scale on it. I don't have time for that. I gotta get going. So here's what I came up with. The bolt, a nut, and a piece of DOM tubing. And what all it's gonna do is we're just gonna use it like a jack. I'm gonna weld this piece in here like this, and then the bolt, I can raise or lower the elevation, fine tune it, because I can lift this up like that. And then when I get it to the elevation I want, take that slot, and this will go in here like that. Then I can cinch up the hose clamp. There we go. It should hold it steady. The bolt shouldn't rotate because this is here and this is here. Starting simple is gonna be the fastest. Oh, we need to lower it. Okay. Beep, 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 beep. There we go. That's the angle. Hose clamper down. And just like that, we're set. I want to be sure that I put these discs through as many real-world scenarios as I can. One variable I want to test is how a flap disc handles hot welds. Will it glaze? Will it melt? Will it catch fire? Will it explode? So what I want to introduce is some heat, and I want to use this. Now, if you've never seen this before, I'll show you how it works. So this is an induction heater that uses fancy gizmos and electrics to run an electrical current through here, and uses a magnetic field, and we can heat it up. I'm gonna crank the amps way up. We won't run at full power. 3, 2, 1, go. Okay, we're heating, already smoking, burned off all the oil, and we're already seeing red. And we'll see if the grinding discs perform better or worse when it's hot. Now that I've got the heat, I need to find a way to hold this probe in place, because I won't be able to operate the machine and hold the probe at the same time. This will allow only the first few inches of the test bar to become red hot, then the probe will turn off. This simulates grinding a hot weld, where only the surface of the metal we are grinding is heated. So here's what I came up with to hold this probe. We have this nice little 2x2 square tube right here, and this 3/4 inch DOM tube. And it just so happens that they fit pretty nicely together. So this is gonna give us some in and out movement. And then I tack welded this nut right here to this little set screw. Ta-da! Super slick. But as you can see, this tube is not in line with this. So we need an extension in between here and the tube. And that's what this is. We have a telescopic tube with a piece of 90 metal on here like this, so we can telescopic up, and then we can roll it like this and gain some elevation, and then just change this. Try to keep it super simple and dumb. So let's tack weld this all together and we'll be on our way. See, like that. This is looking slick. And then we like that. So then we clamp it here, and with a combination of all of those things, we should be able to get it right where we want. To create realistic scenarios for these tests, I need to simulate a human grinding. When applying pressure, humans can sometimes be light and other times heavy. I need to figure out what pressure to use. So I got this scale here. So what I'm gonna do is I'm gonna zero it out, and I'm gonna watch this as I grind and just kind of feel it and see what I'm kind of averaging. I saw like 9 pounds there pretty consistently, 7, 8, 9. So let's just go to 10, how about that? It's a nice good round number. So we need to make a weight that's 10 pounds to put on top. That's pretty heavy. That's a lot of force on one little area. All right, so I think we have this thing tacked together well enough to where we can try a first test and it not completely fall apart. What I want to do is I want to try starting the grinder with the weight already on it. It's going to be much safer than trying to drop this whole thing down on a moving grinder. We're going to see if it has a hard time starting or if it just takes off and goes. And 3, 2, 1. Oh yeah, look at the sparks. Holy smokes. Heck yeah, I think we need a little oscillation. That was pretty awesome. But look at the pressure, see how it just grinds one little spot. It needs some movement. Okay, turning grinder on, and then turning oscillation on. 3, 2, 1, go. Oh yeah. If this isn't scary, I don't know what is. Yeehaw! Okay, so she's stopping. Interesting. It's like it stops grinding after a while. So crazy. Cool. All right, let's try the induction heater here. Hot weld test going on in 3, 2, 1, go. All right, overall success. Whew, smoking hot. That might be a little destructive, but pretty cool. Looks like they eventually get to the same spot. I'll have to play around a little bit, maybe try one with a little lighter weight, see if that helps. But overall, the rig seems to be working. I did a little more testing off camera, and I'm still not quite happy with the way the disc is wearing. So let me show you what we're looking at. We're getting a lot of wear on the disc, which is exactly what I want. But what you can see here is we're getting a lot of glazing and some heat in the center. And when you look at the test coupon here, you can see the bar is really shiny, really glazing over. So what I'm thinking it is the surface area here. It's just a lot of surface area because we're not going to give up yet. We're trying to search for the perfect grind on this disc, and I want this wear pattern to be just right. So I got to thinking, maybe I need to switch the bar. So I'm thinking to switch to like a 3/4 bar that's like 3/16 wide, something a little thinner that the disc can shear off, and maybe we can try moving this back and forth and seeing what kind of results we get with this. So what I've done is I just changed out this little attachment here, and I've just squished a piece of tubing on the diagonal so it can slip in. Now I can replace the square tube version with the flat blade, and we'll give this a shot. And then for temporarily, I ground a tang into the top. We can fit our weight down on there. So let's just take a look, see how this disc wears with this setup, and see if we can achieve that magical hand ground look that a standard disc looks like without any of that heat or glazing. Okay, something interesting is that the flat bar is going to overhang the disc by a little bit on each side, which may not be a bad thing. We're experimenting. It's not like there's a YouTube video or anything to watch on how to do this. Fire this baby up and let's cut something. Okay, it's looking good, but the first 30 seconds always looks good. Okay, looks promising. That's a good sign when you can hear the grinder load up. That sounds like somebody grinding in the workshop right there. Okay. That's pretty good. It's not too bad. Crazy how it's just kind of shaving that off and curling that up. What a weird test. I do like the pattern on the disc. So it's even from this edge to the tip. And you can kind of see how the flaps are starting to feather all the way across. This is a really good wear pattern. I think this is a better representation of somebody actually grinding than this. So if I were to evaluate and say, this guy's grinding better than this guy doesn't know what the hell he's doing. He's just pushing hard right there in the center. So I think I like this flat bar method. I'm thinking I might convert. All right, we got another new bar. We're gonna try a heavier weight. I was wrong, this is almost 12 pounds. But if this can grind without burning up the disc, we're on to something here. Turn it on and try another test. All right, here we go. It'll be a little heavy. She's throwing the sparks. Oh, maybe. That did exactly what I wanted it to do. Just flat destroy it. That is awesome. So that was what? Maybe 30 seconds of straight up hogging. Perfect. So these discs are like, I'm not even gonna tell you how cheap they are. They're like $1. But that's what I wanted to see. Straight up hogging and destroy the disc. See, that's good too. See how the color, it's not blue or shiny, it's getting good grip. I'm gonna say that was maybe 2 inches that it ground down. I should have measured it before. And this is true. This is what really does destroy grinding discs, is corners and stuff, edges of materials. That flat bar is the ticket, man. Pretty cool. I was trying to pick it up with my hand to reduce some of the weight. Probably won't be running 12 pounds. I'm gonna cut this down.
From my experience, grinding can vary from making contact with your material from a flat to a steep angle. I'm gonna have to do some tests to figure out which angle is gonna give me a realistic wear pattern on a disc. So for this first test, I'm gonna use my best judgment and set it at an angle of 5 degrees as a starting point for both grinders with a positive and negative angle.
Turn this sucker on and we're ready to go. Okay, 3, 2, 1, go. Oscillating. Okay, that one's done. All right, take a look at that.
Not expecting that. One's definitely hogging more than the other. Interesting. I'm even more confused than I was to start with. These are supposed to be backwards. So why did this one start to deteriorate first with the angle in the back? I don't know if it's the placement of this on here, which I thought they were exactly the same. We need to run the test one more time. Let's turn and burn. Oscillation on. Starting to see smoke. All right, look at that. 2 even looking discs. That's pretty good. That's what we want to see. But look at that. That is, every time I do these tests, I'm even more confused. Oh my gosh. What this tells me is that this disc is more efficient this way, but nobody grinds like that. The tips always go first. I know, I'm torn. But look at the tip. See how that's nice and square? Obviously this one ran longer to get to this point and it removed this much more material. This one killed the disc faster. Okay, so we went from 5 degrees and I split the difference to 2.5 degrees, positive and negative on each of them. So we'll see how that makes a change. Go. Look at that. That sucker's gonna win chip of the week right there. That thing's sweet. Wearing the disc away pretty consistently. Let's take a measurement. Theoretically, they should be the same. Look it, we did it. We did it, we did it, we did it. Look at that. They are damn near identical. Isn't that cool? Finally getting the results that I want to see. Consistent grinding, the angle bar straight, and our method of bringing the test bar all the way to the edge isn't prematurely wearing that disc. Disc looks nice and flat. It's much slower grinding this way, that's for sure, but the disc wear is consistent. But I think if I keep this method on all the discs, we're gonna have good data. Okay, same exact test, haven't changed anything. The only variable we're gonna do is we're gonna add less weight. So this is 4 pounds, the exact weight of the grinder. And someone says, just let the grinder do the work. This is the work right there. What I'm looking for is hopefully these discs cut with this angle in here. If it doesn't, that's okay. These discs just require more force. Some discs are gonna require more or less, but we need to collect that data. Ready to go. All right, gonna set a timer for 5 minutes.
5 minutes later.
All right. Oh yeah, look at those results. Okay, everything looks good. The disc looks like it's wearing pretty evenly all the way across there. About the same, doesn't matter if it's tilted forward or backwards. The back of the disc is getting the most pressure. But overall, I think we found the magic number again. But tilting forward or backwards does not seem to change anything. So with all the data collected, I'm gonna stick with a 2.5 degree tip up for every single test. This is gonna give me the results that I'm looking for to allow all the discs to wear evenly. So it looks like in that 5 minutes, we removed 3/4 of an inch. Nothing spectacular. I have a feeling better grinding discs are gonna remove more with less pressure, and that is really valuable information that I can't wait to see. So I'm happy with that. I think we're ready to go. So here's the plan. I have a test rig with 2 grinders and a set of test coupons, all in a temperature-controlled environment. On the left grinder, I'll preheat the first couple of inches of a test coupon to simulate grinding on hot, freshly welded material. And then the grinder on the right will handle a regular room temperature coupon as the control. Since pressure may vary in regular grinding, I'll start with a light 4-pound weight on both coupons, letting gravity feed them in. To keep things clear, the preheated coupon's weight will be red, and the room temperature coupon's weight will be blue. I'll then run another set of tests with double the weight to 8 pounds to observe how a heavy pressure affects the discs. And then we grind. Remember, every test will use a brand new disc. To control the grinders from a safe distance, I'll use a control station behind this blast shield. Here, I can start and stop both grinders' rotation. For all tests, the grinders will run at a maximum of 11,000 rotations per minute, a standard speed for most off-the-shelf grinders. Then below that is the control for oscillation. This will allow the platform to move forward and backward a total of 3/4 of an inch, making a full revolution once every 3 seconds or 20 per minute, simulating regular grinding back and forth. Beside that are 2 amperage meters, tracking how hard each grinder is working. I'm aiming for 6 to 8 amps. If it falls, that could mean the disc is losing cutting efficiency. Then above that is the clock. Tracking test duration. So, what data are we collecting? The goal is to measure how much material each disc removes over time, as some discs can lose effectiveness fast. I'll have each test run up to 20 minutes, unless the disc either slows its cutting to less than 1/8 of an inch of material removal in 15 seconds, or if the disc disintegrates, which we will be able to see with the smoke that comes from it. The test coupons have 1/4-inch markings, so we can see exactly how much material gets removed. If a disc runs long enough that I need to switch out a coupon, I'll pause the clock during the switch to keep the data consistent. To capture everything, I'll have cameras at multiple angles. One overhead to view both grinders and coupons. A close-up to see the coupon disc contact point, which will be helpful for measuring. One focused on the disc's surfaces. Another overseeing the full testing setup. One pointed toward the amp meters, so we can collect that data. And one for streaming live on YouTube. And to keep sparks away from the cameras, I'll use cardboard shields. Since sparks may still obscure the footage, I've designed specialized spark diverters to control the spark direction, so we can clearly see what's happening. If anything catastrophic happens, we will need a high-speed camera to capture it in detail, but this requires a trigger, so someone will stay behind the blast shield, ready to activate it. This camera also needs intense lighting, so I'll set up 3 lights strategically around our rig. But with all this equipment, the grinders, cameras, lights, and control panel, I'll have to manage power carefully, snaking cables to avoid overloading circuits. We'll all wear face shields and masks to protect against dust and any potential breakages. I need these grinders to last through all the tests, so a viewer sent in some grease for me to use, and this will allow the gears of the grinders to last even longer.
So here's the sound test before. Now after.
Before and after each test, photos will be taken of the disc so that we can visually inspect exactly what's going on with them. So, each disc will be tested 4 times, with a 4-pound weight on hot and cold coupons, and with an 8-pound weight on both as well. With 31 discs, that's 124 tests, each up to 20 minutes. It's a huge undertaking, but now with everything ready, let's get started. We tested one brand at a time. Because we have 2 grinders, we could run 2 variables simultaneously, and run a cold test and a hot test at the same weight. If one disc failed early under its conditions, we'd turn that one off and continue on the other disc until the disc failed, burnt up, glazed, or reached its 20-minute time limit. And this varied from manufacturer to manufacturer. The discs were then removed, labeled, and saved. 2 new discs, but from the same brand, were then put onto the test rig, but we switched out the weight for the heavier one. If you would like to see this process of how long it really took, you can watch a YouTube livestream video we did, and can see how boring it all really was. Some discs would fail quickly, and others took a long time, but we had to stand nearby the control panel in case anything happened, all day. If Alex saw something interesting happen, he would trigger the high-speed camera, hoping to capture visual data we could analyze later. If a disc performed really well, it would chew through a test bar in a matter of a few minutes. I would then have to remove the short section of bar left in the holder and replace it with a new one, transferring the weight from the old bar to the new bar, making sure the test would keep going. Any gaps from this transition of switching out the bars would be edited out of our data collection, making sure this test was still fair. Some discs stopped cutting pretty quickly, and we could visually identify this a few ways. There would be significantly less sparks. The amp meter would drop to a relatively low number, and the test bar wouldn't have any more material being removed in a reasonable amount of time. This would vary from disc to disc. The shortest I saw one fail was 2 minutes, while others lasted the full 20. Another thing we witnessed was complete disc failure due to damage. Generally, we let the disc go until we saw blue smoke, which meant we were into the glue in the backing pad, and so we'd have to stop the test. In between all the disc resets, Alan would stop every camera and log the disc that was tested to make that media collection and documentation a bit easier to manage, and this added a few minutes to each test. Typically, the 4 tests per disc took between 15 and 45 minutes, so we were only able to test about 6 disc brands for the first day.
So day 1 is complete, and I've learned a lot about this test rig, and I want to show you what I've changed since we built it. So the first thing we had to do was add these guards, at least this top plate on here, because all the sparks were just spilling over and blocking the camera, and that was no good. So what we've done is we've shooting the sparks out this direction on this grinder, and then this side, we're just letting the sparks go free. But that's one modification we've had to do. The second thing we've done is I've changed the probe on the heat element here, and I've uncoupled it from this test saddle. So all I'm doing now is putting the test bar in here and kind of holding it steady for the allotted time of about 30 seconds. And then I turn the grinders on, and then test bar hits the disc, okay? And then I remove the probe and I set it down here. So that's one thing that we've changed, and it seems to be working pretty good. But one of the things I'm noticing is that we're getting a lot of buildup in the guards, so I'm gonna try another experiment. I'm gonna try some weld nozzle cleaner inside of here, see if that kind of helps some of the buildup. We'll see if that works. Another side experiment. So the next thing that we found is we need to be running the test longer. Our original test was set for about 5 minutes, and I figured that would be enough time to grind the bar, but it's actually not. So we've stretched it out to 20 minutes. Now we're blowing through 2 or 3 bars, which is unfortunate because I've cut over 250 bars, and I'm gonna probably need double or triple that. So that's something I didn't take into consideration. We have a whole bucket of shorties, all the short bars that didn't get all blown through. And we do have a little bit of waste that doesn't get all the way through the whole rig here.
The first day was a little slow because we were just getting into the rhythm, but by days 2 and 3, we were averaging 8 discs per day. That's 32 cycles of testing.
Okay, so we just completed day number 3. Whew, dust everywhere. But let me tell you, this is my life. Look at the floor. It is complete mess. We're making piles of chips, if you want to call these chips. Micro dust. Gotta make sure to wear your mask and your face protection. Look at the chips that are coming off of these things. Big blobs. And that's something that I've noticed, that if the disc is producing chips that look like that, it's not a very good cutter. And it generally has fairly low performance. So that's pretty interesting. Look at this. Don't say I don't love you. There's a lot of bars in there. I'm not too happy. Here's why. Some of these discs are really expensive, and I'm really not seeing the performance that I was expecting out of a disc that's so expensive. And the internet says these things are the greatest. I'm trying to understand why they're not really performing up to what my expectations are. And I think it's because we're spinning them too fast. So what I want to do is add one more variable into this equation and turn these discs a little bit slower. But what's that going to entail? Well, I'm going to have to change the grinder out to something where I can slow it down. So here's the solution, a variable speed grinder. I probably should have started with this in the beginning, but you know, you use what you got. These grinders have held up pretty good, but as you can see, we're about another 1.5 inches longer than the standard 11 ampere. Now I have to move my bracket and my motor back a few inches. Not a big deal, but it's gonna slow the next testing process down of retesting some of those expensive discs to see if we can get them to perform adequately. Now here's my thought though. I do think that slowing the grinder speed down is a good thing, but what I do think a good disc should be able to do is go fast and slow, high pressure, low pressure. And I'm probably going to only test the 4-pound load, because what happens with the 8 is that when it's pushing down on this disc, it's slowing the RPM down anyway. It's only when we're light pressure that RPMs are just zinging and going to full max RPM. But I'll play around with it and let you know where I ended up. So we have a successful installation of the new variable speed grinder, but I have another problem. And of course, the story of my life, nothing can be easy. So on the original rig, the toggles were always depressed, pushed down like this. So Alex turns the grinders on remotely. So I go ahead, turn them on, and I can hit the button and go. No big deal. Okay, turn them off. Okay, he's got them turned off. Now I'm gonna push the grinders down. Okay, now hit on. Nothing happens. So the triggers have a reset, watch. That's extremely frustrating. So now every time the power gets turned on and off to the grinder, the trigger has to have a reset in there. One idea was to go back into the paddles here and jimmy rig it, find some way to bypass that safety switch, or I'm just gonna cheat because I'm in a big fat hurry and I'm just gonna place this bar across both toggles like this. Okay, kill. And then we still have the kill switch in the back. Quite unfortunate, but this is the life, this is the story, this is what inventing's all about. Things don't normally go to plan, but we'll make our way through it. And then maybe someday I'll come back and mod these so they work properly. But we're ready to continue testing.
We could tell some discs were poor performers because the coupon would curl up where it makes contact, while the good discs just gave a clean cut. Day after day, this is what the shop sounded like. But all in all, everything went according to plan.
So now that we collect the data, we get to pass it off to Conrad.
First, we start with the cameras, and there's a lot of them. We have to make sure that they're all synced, meaning that they all start at the same time. Both test coupons don't necessarily start at the same exact time, so to keep things fair, we have to manually set both of them to 0. This is going to give us about 10 layers of video data. Then, with each test and timeline, we have to pull 10 different data points, and we pre-selected these data points depending on how long a test runs. If a disk falls short of 20 minutes, it goes into one category. If it reaches the full 20, it goes into another. Then, between these different data points throughout the timeline, we carefully measure how much material has been removed, using this handy little ruler. As an example, we can see this rod being ground away, and I can use this little guide to show exactly how much has been removed. So then I scrub through the footage and count up how much material has been removed between these 2 points in time. Then these numbers get plotted on a graph. If the amount of material between each interval goes down, then that means this disk isn't performing as well as when it started. This graph paints a story of how a disk performed with a single variable. And remember, many of these tests lasted about 20 minutes, but that was just a single variable. Each disk had to be tested 6 times. So that's collecting 6 series of this data. This took around 2 hours per disk just to collect and plug in. And remember, this had to be done 31 times. I gotta get back to work. So I'm going to hand this back to Jason, and he can wrap all this up for you.
So, we've done the tests, and we've got the data. And from what I've learned, there's no simple answer to which flap disk is the best. So this journey is going to continue. Every flap disk I tested is going to get its own video, and I'm going to release them one by one, analyzing the data and comparing them to the reviews that are already out there. Stay up to date on the Fireball forum, because I'll be posting them there first. Thank you guys for watching, and I'll see you on the Fireball forum.